All right, buddy. So just to finish up our discussion that we were having here, okay? At the end of the period, we were discussing this heating curve. And you can see that this is a heating curve for water. And our substance, our water in this case, starts off as ice. And during this section here, you can see that the temperature increases. And x-axis, y-axis, temperature on the x-axis, or y-axis, thermal energy added on the x-axis. This makes sense. As thermal energy is added, the temperature goes up. Okay? That's true. And during this phase right here, it's labeled as water, and we see the same thing. And then up here at the top, labeled as steam, and we see the same thing. But there are these plateaus here and here. And like we said in class, if a plateau on this graph, because temperature is on the y-axis, that means the temperature is not increasing or decreasing. But on the x-axis, thermal energy is being added. So what's going on there? Well, you can see from the graph that these sections that show the plateaus, we have phase changes occurring on. Right? We either have melting, or we have freezing, or we have condensation, or we have vaporization, right? We have phase changes occurring during those times. What we find is that if we monitor the temperature of a substance, when it's undergoing a phase change, the temperature will not increase or decrease. That doesn't mean that energy is not being added or taken away. It just means that even though the temperature or the energy is being changed, the temperature is not. So, what's happening? Well, if you look at your book, okay, if we go back to page right here. Oh, one more. Sorry, my bad. Changing from one phase to another also includes heat. Well, that's true. Heat is an increase in energy, right? But temperature is the average kinetic energy of those particles. So when we see a section like this, like the pink ones on this heating curve, energy is being added, but the average kinetic energy of those particles is not changing. What's going on there is that when we discuss states of matter are controlled by two factors: motion of the particles and the arrangement or the attraction of those particles. When we go from phase changes, what's happening there is there's sort of a quote-unquote rearranging of those particles going on. We're messing with the attractions, or how those particles are oriented in relation to each other, instead of the actual motion of those particles. So instead of the energy being added, the heat that's being added going to changing the kinetic energy of the particles, it's actually going to change the potential energy of those particles. And so we end up with this particles being sort of set and rearranged and stuff like that, so that they can be ready or move into that different phase. We refer to this energy that is not changing the temperature of the particles as the latent heat. Okay? So you can see here on page 371, right, our definition of latent used to describe something that exists but is not yet developed, evidence, or manifest. It's something that's hidden. So it appears that this energy that is being added to our material is just going away. It's not changing the kinetic energy of the particles. And that's true, but it goes into the potential energy of those particles. So we have to account for that energy because of the whole conservation idea. And so we refer to that energy as the latent heat. The energy that is either added or lost by a material that is going from one phase into another phase. And so you can see here on page 371, the heat required to change from one phase to another, Q, right, is equal to M times L. L is that latent heat. And if you look back at the lab that we did on latent heat the other day, you'll see that here, if we looked at, actually, let me take you here. Okay. This is pretty much the lab that we did the other day. We had water, and then we had ice. If we looked at what happened to the ice, we would pick up our lab pretty much right here. The dry ice that we put in first melted when it went into that warm water. And then the temperature increased until it reached equilibrium with the water that was already in the calorimeter. So your job in your lab the other day was to find this heat, the amount of energy that that ice gained in changing from a solid into a liquid before the actual temperature of those particles will start increasing. We refer to that as the latent heat. So here you can see, oh, I shouldn't use that. I should use this because it relates to that phase change. The amount of heat that is lost depends on, or the amount of heat that's gained during there depends on the latent heat plus how much mass we're actually talking about. So those two factors we can use to determine how much energy was actually added to these particles while they're changing phase. And you can see on page 371 that, again, water has a very high latent heat. You can see there's two types of latent heat here: latent heat of fusion, latent heat of vaporization, which hopefully you get is the heat that's being added to an object or during freezing, melting, or during something changing from a liquid to a gas or a gas to a liquid. Okay? Latent heat of fusion, right, it's called fusion because that's what happens when something freezes, even though in the lab that we did the other day we were melting ice. We're just doing that same process but in reverse. So it could also be the latent heat of melting, just depending on which way we're going. All right, so you can see that water, again, has a very high latent heat for both fusion and vaporization, right? Copper, obviously, so some of these metals are actually really hard to turn into gases because metals are hard to turn into gases, right? But you can see from here that the latent heat turning something from a liquid into a gas is much greater than something turning from a solid into a liquid because we have to increase the energy of those particles so very much, and we have to get them away from each other to turn them into the gas phase. Okay? All right, so over the next couple of days, I'm going to have you guys work on a couple of problems related to these topics. While I work with the year ones on a couple of introductory topics, and then we'll get into the next part of this section on gases probably by the end of the week. All right?